Hello guys, welcome to STR8CHEM. In this video, we're gonna talk about strong bases and weak bases. To start, let's have a look at the definition for a strong base. Strong base is defined as the base that will be completely dissociated in aqueous solution, just like strong acid. So the definition of a strong base is this. The key word that you need to look for is completely dissociated in aqueous solution to form negative hydroxide. The only difference between strong acids and strong base is for a strong base, the dissociation will be producing OH minus, which is hydroxide. Hydroxide, if you still remember, this is OH minus. Let's have a look at a few examples. So for these hydroxides over here, it will be completely dissociated. So complete dissociation will be using irreversible arrow, and you will be having OH minus hydroxide plus the positively charged species Na+. Same goes to KOH. You will be producing the OH minus, okay, and the K plus aqueous, complete dissociation. What about MgOH2? So the difference over here, it has 2 OH. So you have 2 OH minus in aqueous plus Mg2 plus aqueous. So this is how you're going to write the chemical equation for strong base. It's similar to what we have looked at strong acids. They will be completely dissociated. So all of it over here, NaOH and KOH, all of the substance that you have in the beginning will be converted into the ionic products right there. Most hydroxides of alkali metals and certain earth metals are strong bases. So we have looked at all the examples. We have NaOH, we have KOH, we have MgOH2, we also have BaOH2. So these are the examples of strong bases that you can find. What about weak base? What is the definition of weak base? If we know strong bases now is complete dissociation, you can guess that for weak base, you're going to have partial dissociation in aqueous solution. Okay, so weak base is the base that will be partially dissociated in your aqueous solution. The keyword, partial dissociation in aqueous solution for weak base. We have a very classic example over here, which is ammonia. And to write the partial dissociation for ammonia, we have to include water, because we have to show that the OH minus will be from water. H from water molecule will be donated to your ammonia. Remember, ammonia at the nitrogen atom, it has a lone pair, and that lone pair will be able to take one of the H in your water molecule to get protonated, and this one will be converted into OH minus. So, as usual, when you have partial dissociation, we're going to use reversible arrow, and right now your NH3 will turn into NH4 plus. The reason why NH4 plus, because one of the H from H2O will be donated to your ammonia right there, and you're going to have OH minus. It's very important for you to remember, for you to show that the solution is in basic condition, we need to have OH minus. That is why we need to show H2O right here. Unlike for strong acid, it is optional if you want to use H2O or not. Now, since weak base has an equilibrium right there, as you can see, that is the equilibrium indication that it is at equilibrium. And yes, this equation here will be able to have a Kb. Kb is your base dissociation constant. So how to write Kb for the reaction that we have over here? It's very easy. It's the same as what we have done for Kp and Kc in the past. So the Kb for the reaction on top would be written as concentration NH4 plus times concentration OH minus. Both of them are 1 mole and 1 mole. Divide by concentration of NH3 aqueous. We're not going to be including H2O liquid here because liquid is constant, therefore it will not going to be part of your base dissociation constant Kb.